When people talk about good weather, they usually mean calm, sunny, warm weather. But if this is the only weather you had, that would be bad. We depend on plants, and for plants to grow, we need weather that changes, where sometimes it rains, sometimes it's sunny, and there's variety. Being able to predict the weather is a fascinating and super useful tool, and it's one that we're getting better and better at over time. Knowing what the weather's going to be like tomorrow, or the next day, or next week is super useful. But how do people predict the weather? And how accurate are our predictions?
I'm Math Dad.
I'm Science Mom.
Today we'll see whether we learn about the weather.
That was terrible. So are we going to learn about the weather today?
I hope so. I don't know. I'm just the sidekick here. I don't know where these lessons are going.
We are definitely going to learn about the weather today. And to learn about the weather, there are three main things that we need to understand: pressure, temperature, and humidity, or relative humidity. Those are the three things that we're going to be focusing on today. But before we dive in, I want to point out that the people who are watching this live stream right now, and you if you're watching the replay, we're experiencing very different weather right now. I checked in the chat, and I looked online as well. For shout out to those who are watching in Alaska. It is very cold in Alaska right now, down negative temperatures in Fairbanks. And then Charlie, Harold, William, and Elliot and Rosa all experienced snow in all across the northern United States and Canada. We're getting a lot of snow right now.
Guess what? My phone this morning said snow in 53 minutes. And we were like, oh, really? Really? And we went out and there was no snow.
We were so excited, and then there was no snow.
So it turns out you can't predict the weather.
That's not entirely true. It turns out that weather prediction it has to do with probabilities. And when it tells you that there's a certain chance of snow, it very rarely says 100% chance of snow, because things can change. And there was a chance. We had a lot of clouds today. There was a chance that it could have snowed, and it was cold. But alas, we did not get any snow.
No snow for us.
No snow for us. All right.
So you were talking about humidity, Science Mom. I know what humidity is. Humidity is how much water is in the air, right? Like if there's a lot of water vapor.
It is the amount of water vapor. But before we talk about humidity, we are going to talk about pressure, because there is pressure around us all the time. If you think about where you are in the atmosphere, you live in the bottom layer of the atmosphere, the troposphere. And up above you, there is a lot of air. And the weight of all that air on top of you produces a certain amount of pressure. We call that atmospheric pressure. And to show you just how strong atmospheric pressure is, we are going to crush some cans.
Whoa.
You ready for this, Math Dad?
I am ready for this.
I am going to put on safety goggles. And do I really have to have safety goggles for this experiment? It's kind of an optional thing, but I think anytime that you have a change in pressure, it's a really good idea if you have safety goggles on.
And I have a towel here to protect the equipment from Science Mom and her nefarious schemes.
Don't worry, Math Dad. These cans right here are empty. And the real question is, did they get hot enough for the air inside them to expand so that the pressure inside the can is really low? I've had them on a hot plate for a little while. We're going to test it out right now by... We're going to test it out by flipping it upside down.
Nope.
Ooh, and this first one did not work. So here's what we need to do.
What do we need to do?
I need to turn up the temperature on my hot plate just a little bit.
And you got it set on low.
Another pan. I did, because I didn't want it to be too crazy hot. So I'm going to get my other cans heated up, and then we'll give it another try.
Do we need to come back in a few minutes?
This can right here, I think, should be hot enough. And the trick with this is I need to flip it over very quickly. So I'm going to get my can ready, make sure I have a nice firm grip, and 1, 2.
That didn't work very well.
Not much seems to be
It turns out there's no air pressure.
Oh, there is air pressure. And that air pressure, because the air in here was hot and the molecules were spread further apart, it actually drew water up into the can.
Oh.
Did you see that?
That was a lot of water. Yeah.
When I first dumped out the can was dry, but now it's not. Now it got filled up with water by the pressure pushing it in.
It's still a little warm.
And it's cold now too.
All right. So should we wait a couple of minutes and come back? Because if the cans are cold, we won't get as good of an experiment.
This is true. This is true. So we're gonna set that up, and we'll talk a little bit about wind, and then we will come back to our pressure experiment. So this demonstration that we're doing with the cans is a very fun one, but it's one that is a little bit tricky. And the best way to do it is to have about a teaspoon of water in the can. And then as soon as that water starts to boil, where you see steam coming out of the can, then you flip it over. So I'm going to kind of keep an eye on these cans. And as soon as I think they're ready, we'll jump back. But before we do that, let's talk about wind, Math Dad.
So just the question for the chat. Do these glasses make me look cool? Just got to know. Okay, sorry. Okay, wind, Science Mom, go ahead.
What causes wind? Where does wind come from?
Okay, so there are these giants that come out of the ocean. They're usually hidden, but when they come out, they've got these big horns that they can blow, and they blow really hard, and it causes the wind. Not many people know this.
It's usually windier over the ocean than on land. This is true, but it is not caused by giants. It's caused by a difference in air pressure. And we can demonstrate this right now using a balloon. Math Dad, if you'll blow up that green balloon for me.
Okay.
The reason a balloon can be inflated is because we're putting extra air into the balloon. We're increasing the pressure in the balloon. And now, if you will let that pressure go, you can create wind and make these ribbons. You see the ribbons move? Math Dad just made wind by letting the pressure out of the balloon. And the reason the air went out of the balloon is because air will always move from high pressure to low pressure. That's true for a balloon, but it's also true for a huge mass of air over a continent or over the ocean. If there's a high pressure area, then those molecules will push towards the low pressure.
And the giants are making high pressure? Or
no giants.
Okay, no giants.
No giants.
What's making high pressure?
What's making high pressure? It's a combination of a couple things. The sun giving energy to the earth, that heat coming in, heats up air, gets the air moving faster, and gets the air moving, and it pushes upward. That's one source of high pressure, is change in temperature. Our water is ready here, speaking of changes. So let's switch our view and see if we have better luck the second time.
All right, Science Mom. I believe in you.
I can see steam coming up from this can right here. So I'm going to carefully grab my can and... Oh, I don't think I was fast enough. Better luck with the second one. All right, I'm going to scoop this one right here. I told you this experiment is a little bit tricky. There we go.
Whoa.
Third time's the charm.
Wait, did you squeeze really hard?
I did not squeeze at all.
You just sat it in the water?
I just sat it in the water, and the air pressure that is around the can all the time pushed it in because there was less air inside, because that air inside had been so hot.
So it like imploded, like the opposite of an explosion blowing outwards. This one kind of blew inward. That's the air outside that was crushing it?
Air pressure, yes. Should we try it one more time? I have one more can here.
Yes.
And I think it's ready. 1, 2, 3.
I saw that one happen. You didn't squeeze.
I did not squeeze.
I'm a witness. Whoa. Well done,
Isn't that amazing?
That's impressive.
And to show that I didn't do it by some type of trick of squeezing the can, let me turn this one upside down, and then I'll try squeezing.
Whoa, the air pressure is stronger than science, Mom.
It is, it is. That was my best. That was me squeezing it as fast as I could. And you could see that I could not crush the can as well as the air pressure could.
Oh no, got some lag, unfortunately.
All right, let's go back to our main view.
All right. So question, Science Mom, is that something that they can try at home?
If you want to try this experiment at home, this is definitely one where you want to have adult supervision, because you have to get this can very, very hot. And you don't want to get the can up to a hot temperature without making sure that you have, oven mitts and other safety precautions. But yes, this is one you can try at home. And all it takes is getting about a teaspoon of water in the can, making sure that you see a little bit of steam coming up and that can is really hot, and then immediately turning it upside down and putting it into cold water. But as you can see from our first attempt, It's a little tricky and it doesn't always work the first time.
All right. I'm going to make sure my kids are not on the internet competing with us, but yeah,
when we're talking about pressure in the atmosphere, we talk about it in terms of barometric pressure. And barometric pressure is because there are things called barometers that we use to measure the pressure. Because if the pressure around us changes, that can tell us a lot about what weather is coming. And almost always, before a big storm moves in, the pressure will drop. And if the pressure where you are is dropping, that usually means that something is coming, because wind will go from a high pressure area to a low pressure area. And most often, if there's a big drop in the pressure, then that's what happens before a storm moves in. And the concept of barometric pressure, we could talk about for a whole entire class. It's really interesting, but I want to keep us just on those three and make sure we cover each of them. So barometric pressure is the pressure in the air. It's how many molecules you have.
So it's atmospheric pressure.
Atmospheric pressure.
Same term?
Yes.
Okay.
And you remember from talking about the layers, down at sea level, we have a higher pressure than we do up at the very top of the atmosphere, where there aren't as many molecules. But you also can get a change in pressure based on temperature and wind, how the air is moving. That can change the pressure too. And when you watch the weather report, they'll talk about that sometimes. They'll say there's a high pressure front coming in or a low pressure front coming in, and they mean there's a big movement of air coming. And that air, if it has more molecules packed in, it's higher pressure. And then wind speed we talked about. The next thing we need to talk about is humidity. And Math Dad, it turns out that cold air cannot hold as much water as warm air. And this is why when we talk about humidity, we don't just say, oh, there are a couple million molecules of water in the air. We don't tell you the actual amount of air. When you look up the humidity, it will be a percent. And it's the relative humidity. And they're telling you it could hold this much, but we're at 50%. So it's how much water is in the air compared to what it could hold.
Okay, so you said warmer temperatures can hold more water?
Yes.
Than colder temperatures. Okay, I wonder why that would be.
That wasn't a mess, Math Dad. Don't worry about it.
Okay, so, does it have to do with the fact? So when water gets warm, it can boil and turn into a gas.
True.
Whereas, so if the temperature were cold, would it be harder for the water to stay as a gas? Because it would want to change back into a liquid? Is that?
It does relate to that. So when it's cold, the water is not going to have as much energy, and air that has more energy can hold more water. That's one reason. But to show how this works, we're going to do a quick little demonstration. And Math Dad, I'm assigning you to be cold air. Cold air is kind of like a sponge that has a whole bunch of rubber bands around it and has been squished.
What are you going to be then?
I'm going to be hot air.
Science mom's hot air. She's blowing hot air.
And I am like a full sponge that has not been squished. And now we're going to show you how much water the hot air can hold versus the cold air.
Ooh, got some colorful water here.
Yes. So I have 2 jars here, one with representing cold air, one representing hot air. Here, scoot the cold air closer to you, Math Dad.
Oh.
And then we're going to see how much water can we pick up with our sponges.
Okay, so the temperature of the water is actually the same. This is just
This is just to represent.
Okay.
So this sponge is a big sponge. This sponge here is the exact same size, except it's been squeezed with rubber bands. Which one's going to be able to pick up more water? Let's put them in.
So it would make sense that you'd be able to hold more because you're expanded more. There's more gaps.
Yeah, there's more gaps in this sponge.
Okay, and somehow the atmosphere is the same way. When the air is cold, it just can't hold as much water.
So this sponge is saturated. It's at 100% with how much water it can hold. Is your sponge also saturated?
Yes, I can't get any more water in there.
Can't get any more water. So this sponge represents hot air, and I'm going to squeeze it to show you how much water it can hold.
That's a lot of water.
That was a lot of water. Now, Math Dad, your sponge represents cold air. Let's see how much yours can hold.
All right.
It's also saturated.
Oh, man.
Not nearly as much.
That was really anticlimactic.
One more time. So we're going to get our air completely saturated so it has as much water as it can hold. If the air is hot, this is how much. Now you do yours, Math Dad.
The air is cold.
That's how much.
Oh, that's pathetic. All right, so that's really interesting, though. The air at different times can hold different amounts of water.
It can. And as the air cools, it loses its ability to hold as much. So if we have really warm air, let's say our air is 90 degrees Fahrenheit, that's nice and warm. And let's say that it's at 50% humidity. So here is our warm air. It's at 50% humidity. It's 90 degrees.
So that's
really warm.
50% capacity in some sense.
So that means it's holding half as much air as it could. If we cool this air down, that's like pouring it into a smaller container. And if we cool it down pretty soon,
then it's at 100%.
Then it's
Stop pouring. Stop pouring.
Then it's at 100%. And what happens when we get to 100%? It's okay, Math Dad, there's a bucket right here to catch it.
Oh, yeah, I'm sure. All right.
When we get to 100%, then we get rain or fog.
Aha.
At 100% humidity, the air cannot hold any more water, and then the water is going to condense out of the air. And you could form fog, just like a cloud at ground level, or you could get rain, a drizzle of rain coming down, or you could have dew form on the ground. Have you ever gone outside in the morning and the entire surface of the ground is covered in tiny little droplets of water?
Yeah.
That is dew, and that's why they call this the dew point. When the air has 100% humidity, that's called the dew point.
Whoa, okay. So the air cannot hold any more water at that point.
Yes, the temperature where the air cannot hold any more water, that is called the dew point.
And so a lower temperature will have a lower dew point because it won't be able to hold any more water.
So let me give you an example. Let's say you're in Alaska right now, in Juneau, Alaska, and let's say that it is 32 degrees Fahrenheit. That's 0 degrees Celsius, the temperature where water freezes at.
Mm-hmm.
If it is 95% humidity, are you going to feel really like, oh, it's so humid? Is it going to feel muggy?
Well, it can't.
It would
have to be 100% before the water. I don't know.
It's actually not going to feel very muggy because the amount of water in the air is kind of small compared to how much you have when it's warm. And will it snow? Probably. If it's 95% humidity, chances are good, if you have good cloud cover, you could get some snow soon.
Okay.
But if you are in Florida and it's 95 degrees Fahrenheit and you have 95% humidity, is it going to feel really humid and ugh?
So at a higher temperature, there would be a lot more water in the air. So that would be a muggy.
Yes, it's going to feel very, very humid. And in Florida, if it's 95% humidity and the temperature is 95, the dew point is probably going to be like 75 degrees Fahrenheit. The dew point is going to be really high. But in Alaska, where it is 32 degrees Fahrenheit, the dew point is going to be pretty low. It's not going to be a high dew point.
Okay, I saw a really interesting question in the chat there. Why is there dew in the morning and not in the afternoon?
Good question. And it's because the temperature drops at night and you get the coldest temperature of the day right before the sun comes up. And so if you have a lot of humidity in the air and that humidity, the temperature is close to the dew point and then it drops below the dew point, that's when you get dew.
Okay, that makes a lot of sense. All right, that is really cool. And so the conditions where we would be getting dew are also conditions that would be consistent with rain?
You could get fog or rain at the same, yes. So sometimes you get dew, sometimes you get rain or fog. It depends on how the temperature is. If the ground is colder than the air, then you'll definitely get dew. If the ground is warmer than the air, then you'll get fog.
Oh, I had no idea.
Yeah.
Okay, that is really cool. All right, so here in Nevada, we almost never get fog. And the reason why is because the water content in the air, the relative humidity, It never gets very high.
It's pretty low. Our relative humidity is usually between 10 and 20%. It doesn't usually get higher than that. And so we don't get dew very often. We don't get fog very often at all.
So that would be like the sponge. If we just drizzled some water on it, it's not ready to leak out. It wasn't saturated.
Yes. And in the summertime, our sponge looks like the big one. It's got lots of capacity for water, but there's just not much water in it. And in the wintertime, our sponge is the smaller one, and it can't hold as much water. So that is relative humidity. And once you know the humidity, the wind speed, and the temperature, you can start to make some predictions. But there are a couple other pieces that you need to have, and one of them is cloud cover. And we're going to share our screen real quick and show you guys what the cloud cover looks like right now. This is updated. This is a website that is updated every 10 minutes using satellite data. So right now, if we look at the United States and Canada and parts of Mexico, you can see that we have a storm coming in off of the ocean, and there's a little swirl there with a cool wind pattern. Most of the United States is covered in clouds right now.
And so that's real time.
Real time. Real
So
time.
if I go outside right now, I would likely see clouds.
Yes. Yep. If you go outside right now, it should be cloudy, unless you're in Texas. Texas looked a little more sunny. And when I say real time, it's about 10 to 20 minutes delayed, but it is gathering data from satellites all the time.
And are people able to make predictions based off of seeing that?
There are two things that we have to make predictions for weather. One is data from our satellites, and then the other is data from weather stations that are on the ground. And then we combine those two things and put them into models, because it's not enough just to know all of the different measurements of how much cloud cover there is and the wind speed. You also need to have a model that can predict what's going to happen next.
Oh, there's some math involved.
There is some math involved. And that prediction is a little tricky. Let's go to the notes. I believe we are on page 14 of the notes. And first, Math
16.
Dad.
Oh, yeah.
16? Math Dad drew a picture of his favorite weather. Can you guess what his favorite weather is?
Let us know in the chat if you can guess what my favorite weather is.
My favorite weather is actually rain. I love rain. But it looks like Math Dad's favorite weather, I'm guessing, is sunny.
It is indeed. Well, I don't know. Those are clouds up there. I don't know if you can tell, Science Mom. That's the problem. Weather is a really hard thing to draw. Oops, I meant to use my highlighter. Yeah, I've got some clouds here. I kind of like it overcast, around 75 degrees. Basically what I think of as spring weather. Yeah.
I like that type of weather too, but my favorite type of weather is rain. And in this page of the notes, I hope you will take a minute and draw your favorite type of weather too, and then see if somebody can guess what it is. Victor guessed sunny. HS mine guessed foggy, and
slightly sunny, just slightly overcast.
And that is correct for Math Dad. He likes partly cloudy days. That's his favorite weather. Now, what I would love for you to do to learn more about the weather is to test the forecast. So we have a page here in the notes where you can write down the 10-day forecast. And if you go to weather.com or any other weather forecast site, it will give you predictions for about 10 days. Write them down and then write down what you observe. What is the high temperature of the day and the low temperature of the day? How humid was it? Did you actually see rain or not, if there was a chance of rain? And you can even include the wind speed and some of these more detailed things as well. And you should notice some interesting patterns. The first few days will probably be pretty accurate, but as you get further and further down, it's not going to match quite as well, most likely.
Okay, I want to make sure I understand this. So you're saying that in these boxes here, they can write down what the current forecast says. So they could fill this whole thing out today.
Yes.
And then once this whole thing is filled out by looking to see what the predicted weather is, then after the day has passed, they can come back and see, all right, here's what the actual temperatures were, and here's what the actual wind was, or they can get some of that data, and then they can compare.
Yes, and then compare them.
But so that you have to wait until the day is passed, and then you can come back and fill out the column on the right.
Exactly.
Gotcha.
And I'm curious if anyone has an idea about why we don't see weather forecasts that go more than 10 days. How come you can't look up a weather forecast that tells you what the weather is going to be like 2 months from now?
It's a really good question.
It has to do with the limits of our models. So our models right now, 10 days is as far as we can predict with it still being mostly accurate. But after 10 days, we lose that accuracy. But scientists who study weather, and they're called meteorologists, they're constantly working on ways to improve the models and get our weather forecast to be more accurate.
Well, what was the name of that website, Science Mom, where you saw the clouds?
Zoom Earth.
Zoom Earth.
Zoom Earth is the name of that website.
So just type Zoom in Earth into the search bar. It'll be there. All right, Science Puppy, are you ready to learn about some weather? Yeah.
I think he is. I have a couple pictures to show you guys, and then we will do our Where in the World mystery, and then we have some quiz questions for you guys. So our Where in the World mystery here. But before we do that, I did want to answer one good question that came in the chat, was about how do clouds stay in the sky and how long does it take clouds to form? And you can see from this time lapse that clouds are usually moving. There's usually a prevailing wind up where the cloud is that is moving it in one direction. And the cloud is forming and it is unforming kind of at the same time. So if you do a time lapse of clouds, you'll see that parts of the clouds are getting bigger and part of the cloud sometimes will be disappearing. And it all depends on those water droplets, on whether you have those droplets growing bigger or if they're evaporating and getting smaller, because those tiny little droplets can also go back to being a gas. So clouds are really interesting and dynamic, and how fast they form can change. But how does a cloud stay up in the air if a cloud can be so heavy? What do you think, Math Dad?
Well, those drops were pretty light, weren't they?
That's the thing you have to remember.
The droplets, we talked about last time, how they were teeny tiny compared to a drop of water, which would fall like a raindrop.
If you look at a cloud, you might be tempted to look at the entire cloud and say it's all stuck together. And it's not. If the entire cloud was all stuck together and each molecule was bonded to the other molecules, it would fall out of the sky right away. It would be way too heavy. But the cloud is a collection of really tiny water droplets. Think about how small a raindrop is. Raindrops are really small.
Yeah, they're tiny.
And the average size raindrop, if we blew it up to be this big, then a droplet of water that makes up a cloud would only be about as big as a grain of rice. That's really tiny compared to a raindrop. So that's how clouds can stay in the water.
In the air.
In the air. That's how clouds can stay in the air.
Yeah, that's a really good question.
And now it is time for our Where in the World mystery. This city of stone in Jordan's desert is accessed through a narrow canyon. Its pink sandstone tombs contain Al-Khazne, the treasury. Any ideas, Math Dad? Where is this location?
Well, Jordan's desert makes me think it's got to be the Middle East. But
what is it called?
What is it called? Oh my goodness. Pink sandstone tombs. I have no idea off the top of my head. I'm hoping the chat can help me out here, because I do not know.
And it is Petra.
Ooh, yep. Nicely done.
Good job, Minor Master.
Minor Master.
Petra is correct. So this formation is one of the most famous ancient heritage sites in the world. And the most famous building that you'll see is this one that is drawn in the picture, which is called the Treasury, or Al-Khazne. But if you look at a map of Petra, Petra is enormous. And that blue circle is around the representation for that famous building, that one tomb. But there are so many different buildings, almost all of them made of rock or carved into rock.
So that's where I think Indiana Jones and the Last Crusade, that's got to be.
Yes, that was filmed there.
That is so cool.
And take a look at this, Math Dad. This is just one passage. There are dozens of areas like this where you have building after building after building carved in the stone.
Wow.
There were more than 20,000 people that lived in the city of Petra hundreds and hundreds of years ago. And it's worth asking, why isn't it a big city now? If hundreds of people lived there so long ago, how come it's not one of the biggest cities in the Middle East now?
Boy, they couldn't get the Wi-Fi into the rocks,
no.
So they didn't want to live there?
No, it has to do with water. In about the year 300, there was an earthquake, And the earthquake shifted things so that their main water supply kind of dried up. And that's one reason. There was also some political things going on that led to the decline of the city, but it was abandoned because they ran out of water. That was really why.
Oh man.
Why
might be a lesson in that for us today.
Yep. All right. If you are watching live, I hope you'll go to itempool.com/sciencemom/live. And if you're watching the replay, if you go to Science Mom, Earth Science at the Science Mom website, then you can participate in the polls. We've got some questions for you.
Or we will update the link down in the description after the live stream. All right. All right, here we are. Today's the day, Science Mom. I'm going to stump them.
I don't think you're going to do it, Math Dad.
No?
I think they've got this.
All right. So for our first question, what do you call a scientist who studies the weather?
Is it a climatologist, a cartographer, a meteorologist, or an astronomer?
All of those are big words. You call them crazy?
Nope.
No?
Nope. Studying the weather is incredibly important. If we didn't have people to study the weather, we wouldn't be able to grow crops as well, because all of our food comes from plants, and being able to grow, have plants survive and grow crops, that depends on the weather. And then we have severe storms too that we'll talk about next week. Being able to know that a hurricane's coming.
Oh, that would be really important.
Yeah, super important. Let's go ahead and finish and reveal.
All right. Answers are still coming in, but they're slowed down. The answer is a meteorologist.
Great job, you guys.
Yeah, meteorologists study the weather. What does a climatologist study?
A climatologist studies the climate, and we'll talk more about this next week, but the climate is very different than the weather. With the weather, it rained yesterday in Las Vegas. So if you extrapolate out and you think, okay, it rained yesterday in Las Vegas must be a pretty rainy place. The climate of Las Vegas is rain.
No, that's not right.
You'll be so disappointed, because we only get rain a few times a year in Nevada. Climate is what the weather's like most of the time, and weather is what's happening on any given day.
What's a cartographer?
Someone who makes maps.
An astronomer?
Studies the sky and the stars.
All right, that was an easy one. You guys got that one right. But what is the term used to describe the actual amount of water vapor in the air? Is it mugginess, barometric pressure, relative humidity, or water vapor percentage?
Good question.
Yeah. They got the last one right, but they're not getting this one right, Science Mom.
Oh, I think they've got this one.
I don't know. All the categories are getting some votes, although there is one lead category. Oh, that bar just keeps whacking me in the head.
I'm going to say real quick, Kate asked a great question. Does water affect the air pressure? And the humidity does change the way the air behaves. Humid water is going to behave differently. Humid air is going to behave differently than dry air. But the air pressure is just how many air molecules you have in a given volume. And water is a gas when it is in its vapor form, when we're talking about humidity.
So that's increasing the mass of...
Yep. And so it behaves a lot like the other air molecules.
Gotcha. All right. They said relative humidity.
Correct.
Okay, you got that one right too.
Good job.
Not bad, chat. All right.
I think we're going to have to see a defeat dance, Math Dad.
No. Because I don't think they're going to know what happens at 100% relative humidity.
I bet they do. Can they choose more than one?
On this one, they can. So the options include wind and fog and lightning and rain. So yeah, what would happen at 100% relative humidity? Okay, I'm definitely seeing two categories getting a lot of votes here. Really is fun to watch those votes come in.
Careful of those bars, Math Dad. Oh, they got you.
They could have put a rounded corner on those or something, because they're so jagged.
Let's go ahead and finish and reveal.
All right. The chat says fog and rain.
That is correct. So when you get to 100% humidity, you will either have dew, fog, or rain, because that's when the air has as much water as it can hold for that temperature. But what if you're at 95% humidity and all of a sudden the temperature goes down?
Ooh, in that case, the dew point is going to drop, right? So that means that the
you'll
water
go below the dew point.
Oh,
So if I have a tub of air and it's 95% humidity, and then I make the temperature drop 10 degrees, I'm going to get condensation.
Right.
I'm going to get fog, or I'm going to get dew all around inside the container. What if I increase the temperature?
Then no fog.
No fog.
Wait, okay, so if I pull a glass bottle out of the fridge and leave it on the countertop, that's going to get condensation, right? Is that related to what we're talking about?
It is. And let's talk about it more after we do our next question.
Okay, get this next question going here. Barometric pressure often drops before a storm. Is that true or false?
True or false?
So back to that question, what's causing the water to condense on the outside?
It's because this bottle is a cold bottle,
Colder.
and it's below the dew point. It's below that temperature where the water can condense. And so the water molecules, they get close to that container, they condense on it, and then more condense on it, and you get water droplets.
In a humid place, I would get more condensation than in a non-humid place.
Yes.
Ah.
If you live in Florida or somewhere else that's very humid, you'll notice when you take something out of the fridge and put it down on the table, you get a little wet spot underneath it. This is not something that happens to us very often in Nevada. Nope.
All right. The chat says true.
Correct. One more question, Math Dad. Get that victory dance ready.
These were just warm-ups. Because the toughest question of all is one that we didn't tell you the answer to. So, what is the windiest place on Earth? Is it Chicago, Illinois, Commonwealth Bay, Antarctica, Topeka, Kansas, or Tucson, Arizona?
Which one of these is the windiest? This is a good question. And if you know a little bit, well, never mind.
Never mind, yeah.
Never mind. I was going to give a hint, but then I knew Math Dad would not appreciate it if I gave a hint.
No, they're going down, Science Mom. They only get the questions right if you give them the answer.
I wouldn't be so confident because that bar just went over the top of your head.
Yeah, there's one bar, but it's probably the wrong answer.
Let's find out.
They're probably picking the wrong answer. So the right answer.
It's correct.
Oh, no. So the windiest place on Earth is Commonwealth Bay, Antarctica. How windy is it there?
It is incredibly windy. We're talking about winds of over 100 kilometers per hour regularly.
Wow.
Regularly.
Okay, that is way fast.
The reason why it's so windy is because you have air that is super cold by the pole, by the South Pole, and that cold air sinks and you get high pressure pushing out towards the edge of the continent. And so you have this constant source of really cold air that is flowing down Antarctica.
Wow. Okay. Well, okay, but Chicago, Illinois, that's called the Windy City, right?
Chicago is also very windy, and so is Kansas. Those are two cities that are among the windiest cities in the United States. Tucson, Arizona is actually the least windy, one of the least windy cities in the United States.
So that one didn't get very many votes. Yep. All right.
So, Math Dad, I think you're trying to forget about the defeat dance.
Fine, I'll do my defeat dance.
It's time for the chicken floss.
You guys got lucky this time. Next time, it's not going over so well. All right, here goes.
The chicken floss. Good job to our chat. And if you watched the replay and got those questions right, well done. Now, we did have a couple questions come in, and one of them that I want to answer real quick is pressure going from high to low, does that make hurricanes? This is a good question that kind of ties in, and let's go back to our other view, that ties in a bit with what we'll be talking about next week. So real quick, I just want to re-emphasize what it means when we're talking about air pressure. So air pressure changes from low elevations to high elevations. Remember, if you took a water bottle to an elevation above 14,000 feet sea level, and then you close the lid, as you come back down closer to sea level, the bottle will get squished, just like our can got squished, because there's more pressure outside, and inside there are not as many air molecules. Now, when we have low and high pressure in storms, that can create these cycles. And we'll talk a little bit more about cyclones and about a vortex and how that works next week when we talk about hurricanes and tornadoes. But the high and low pressure is definitely part of it. Good question.
I mean, it really is cool that wind is such a natural thing, and that it doesn't matter whether you live in mountains or on flat plains, and wind happens everywhere.
Yeah.
The air moves.
Amy has a great question. What's the worst kind of weather? This one's more of a matter of opinion, but I would say freezing rain is probably one of the most dangerous types of weather. So if you take severe storms and just sort of push them to the side because they're kind of unusual, freezing rain is incredibly dangerous because it puts a layer of ice over everything and it can break tree branches and make travel really difficult. And then Tawny Official asked a great question. Why do some places have smog? So we talked about fog. Fog is when you have water vapor in the air that condenses into little droplets. And it turns out that if you have air pollution in the air, you can have a little bit more of that happening, and you can get drop particles that are a combination of water vapor and pollution. And oftentimes that is called smog. And if you live on the island of Hawaii, they have what is called VOG, V-O-G, for volcanic gases coming out that produce air pollution that we need to be concerned about. But smog mostly comes from burning fuels and other pollutions that are put up into the air. Sulfur dioxide compounds can be a big source of that as well.
But smog also has the water vapor in there too. It's a mixture of the pollution and
the water vapor. When you see it, like when you see a layer of it, yes, you've got that mixture of fog and smog. All right, and then one other question. Millie asked, what's the biggest kind of cloud? The biggest type of clouds are cumulonimbus clouds. Those are ones that can be almost the entire height of the troposphere. They get enormous.
That's a pretty cool word, cumulonimbus.
Cumulonimbus.
I remember reading it in my textbook as a kid, and I was like, ooh, cumulonimbus. And that doesn't sound nearly as cool as cumulonimbus.
That's definitely a better way to pronounce it. Thank you for joining us, you guys. I hope that you enjoyed learning more about clouds. And I do want to give a special birthday shout out to Sierra in Canada, who had a birthday on Monday, and Maggie, who has a birthday today. Happy birthday, Maggie. Happy birthday. And if you would like to have a birthday shout out for our registered students, just email us and we will get those in our calendar. Work hard, grow smart, and we'll see you on Friday.
Bye.